Take a look at this function. It's a fraction, and notice what would happen if we replaced x with 2. In the denominator, we would have 2 minus 2, 0. 2 times the 0 would be 0. The function is not defined at x equals 2, and yet we want to find the limit of the function as x approaches 2. Now, x approaching 2, that's an interesting idea. As x gets really close to 2, we want to find out what value f of x is approaching. And that's what limit is all about. So and the request for the idea is this, that the limit as x approaches 2, that's what this notation means, the limit as x approaches 2 of this is equal to what number? And all it's saying is, all this means is, let's take a look at the situation as x gets close to 2 and evaluate what the function is getting close to. What is the functional value getting close to? Now, there are several ways of finding a limit. A couple of ways are by looking at a table of values and by looking at a graph. We're going to do both of these now, and later we'll investigate some analytical approaches or some algebraic approaches to the idea. Let's take a look at a table of values right quick to get the feeling for this. Here's a table involving the previous function. In this row, I've got values of x. Now, just take a look in the middle of it. Here's 2. Here's our sort of our target point. And we are approaching 2 from values above 2 and also from values below 2. And that's the idea of the investigative process of limit. We are approaching the target point from both sides, and we want to know what value f of x is approaching from both sides. All right, so now notice in this row I'm finding f of x, and notice the values here. So I'm looking at, as x gets close to 2 from the left, f of x is getting close to, well, let's see, 2.95, 2.975, 2.99. It looks like f of x is getting close to 3. And over here on the other side, as x gets close to 2 from numbers or values just above 2, just bigger than 2, then f of x is getting close to, well, let's see, 3.05, 3.025, 3.01. Well, again, f of x is approaching 3. Graphically, we can see it very clearly. This same idea is we can see very clearly by using a graph. It's the notion that as x is getting close to 2, the f of x is getting close to 3. And that's the investigative process of limit. All right, here's 2 on a graph. So as x gets close to 2 from the right, f of x is getting close to this 3. This is the level of 3 right here. And as x gets close to 2 from the left side, f of x, again, is getting close to 3. So we can say then that the limit as x approaches 2 of this function is 3. And yet, f of 2 is not defined. It just doesn't exist. This is one of the classic situations. I'm going to show you a number of situations involving limit. But the easiest situation is where the function is defined at the target point and the function is continuous at that point. Now just think of, we're going to define continuous a little more formally later, but continuous is as we would expect it to be. There aren't any holes in the graph if the function is continuous in a particular interval. Consider an interval, well, let's see. But let's find the limit as x approaches 0. As x approaches 0, same function. Let's find out what that is. As x approaches 0, come on over here. Here's 0. Now, as x approaches 0, as our value of x gets close to 0 from both sides, what is f of x approaching? You see, f of x is coming close to what value? Well, this value. You see, and it's pretty easy to figure out that value. The function is defined here. We could just take f of 0 and find that number. F of 0 is 2. That is, the point 0, 2 is on the graph. The function is continuous in this little interval, so it's very easy to calculate that limit to be 2. Here's another situation. You may be thinking now, well, gee, we have to, if we can find f of the target point, then that's the limit. Not so. Here's an example. Here's the same function, or a pretty similar function. I'm defining it in a couple of intervals or in two pieces. F of x is what we had before as long as x is not equal to 2. But we're going to define f of x to be 5 when x is equal to 2. So here's what the graph looks like. You see, so the graph, or in this part of the definition, the function is undefined when x is 2, but we're defining x to be 5 when x reaches 2. So f of 2 is 5. But is that the limit? No, because the limit idea, the limit investigation is what is f of x approaching as x approaches that target point. That's the idea. So once again, just like before, we're talking about as the x approaches the value 2, you see from both sides, f of x is approaching the value 3. Not this value, but the value 3. So still the limit is 3, even though f of 2 is not 3. That's okay. All right, here's a situation where the limit doesn't exist. And it's pretty easy to see why. Our target point, again, is 2. And notice that the function is defined on intervals here. It's a constant function on both of those intervals, but it's a different constant on this interval than it is on that interval. So it's pretty easy to see that as x approaches 2 from the left, f of x is approaching this level, and incidentally, this is 3. So the limit as x approaches 2 from the left, and this is the notation for that idea, as x approaches 2 from the left of f of x is actually 3. But the limit as x approaches 2 from the right, well, let's investigate up here. As x approaches 2 from the right, you see f of x is up here at 6. So we're approaching the 6. So the limit from the right is not the same as the the limit from the left is not the same as the limit from the right, so we say that the limit itself generally does not exist. Before I show you the next couple of examples, let me tell you where we're going with our discussion. We've been talking rather informally about situations involving limit, and we've been examining limit graphically and with tables. And after we go through a few more examples, couple more examples, we're going to take a rather formal approach. We're going to define limit rather formally and see what that arena is all about. But we need to get a feeling for limit and what it's all about graphically and within an equation before we do that. All right, let's look at a couple more situations where the limit does not exist. There are actually 3 classical situations. Here's the second of them. We just looked at one. And here we have a graph, we have an asymptote, and let's say that this is our target point. And notice that when we approach the target point from both sides, as we approach from the right, f of x is going up without bound. As we approach from the left, f of x is going up without bound. So the function is approaching infinity as x approaches our target point. And that's another situation where the limit does not exist. Here's a list of all of the situations that we'll be discussing where the limits do not exist. Limits do not exist when f of x approaches different numbers from left and right. So when x approaches from left and right, we have different numbers for f of x. We looked at that just a little bit ago. And here we had a situation where f of x approaches infinity, and it's also true for f of x approaching negative infinity as x approaches the target point. So as x approaches target point, f of x is approaching infinity or negative infinity. Limit does not exist. A third situation is that f of x oscillates between 2 fixed values as x approaches the target point. So as x is getting close to the target point, the function is actually oscillating, is actually going like this. An example of it is here, that the function is sine 1 over x, and we're thinking about the limit as x approaches 0. Now, this is an oscillating function in the neighborhood of the target point, and we can kind of get a clue about the oscillation if we look at this table. Now, I'm thinking of x approaching 0. All right. So we go out here, we go all the way out here to 1/10, and then we go to 100th, 1,000th. We're getting closer and closer. You see we're getting smaller and smaller. We're approaching 0. All right, what about 1 over x, though? Well, 1 over x, the reciprocal of 1/10 is 10. The reciprocal of 1/100th is 100. The reciprocal of 1/1000th is 1000. Now, it's pretty easy for us to take the sign of each of these numbers. The sign of that number is a value. The sign of this number is a value. The sign of this number is a value. But think more in terms of what's happening sort of with the graph in this interval. Now, understand that the interval for x is just this little short interval. But we're taking the sign of these numbers, you see. And think of taking the sign of all the numbers between 10 and 100. That's an interval that we're taking the sign of 90. Now, in that interval of 90, how many sine curves do we have? Well, let's see. We have one period of the sine curve every 2 pi distance. 2 times pi is 6.28. So every 6.28, we have a period of the sine curve. So that sine curve is going up to 1 to -1, 1 to -1, and so on every 6.28. There are 14 cycles of that sine curve right in this interval. So in this interval, the interval over which we are taking the sign of those values, there are 14 cycles. Now, think about these values, 100 to 1000. Now, although the interval over which we're considering x, this interval is larger than that interval. Here's a smaller interval than that is, and yet we're taking the sign of numbers in a longer interval, you see, because of this reciprocal idea. So between 100 and 1000, if we take the sign of all the numbers in there, we'll find that we have over 143 cycles of the sine curve. So graphically, this, the graph of this function is starting to wiggle a little bit out here, and it's starting to wiggle a great deal, and it wiggles even more as we get close to 0. More and more and more as we get close to 0. Let's look at the graph. Here's our function, and I've made window settings of x minimum -5, x max of 5, and the y minimum and maximum are at the bottom and top of the amplitude. The graph looks like this. You see, there's just a little disturbance here in the middle of the graph. The graph looks kind of normal out here and over here, but right in here there's kind of a disturbance. Let's concentrate on that disturbance area by coming into, oh, let's say -1 and 1. Seems to be more disturbance. Let's come in a little more. How about -0.1 and 0.1? Well, it's even more disturbing the closer we get, it looks like. And as a matter of fact, the calculator isn't even able to show us a clear picture of all of the cycles that will occur as we concentrate on or magnify the interval right in this region of the coordinate plane. There are just too many cycles for the number of pixels on the calculator to be able to display what's really going on. So no wonder we have a limit that, that just doesn't exist. Now that we have a pretty good idea of what limit is and how to calculate limit in a rather informal way, we want to define limit formally. We want to write a definition for limit. Now, the trouble with a definition, or the difficulty in writing a definition like this, is what does it mean to for x to approach c? You see, for x to be arbitrarily close to c, or for f of x to be arbitrarily close to the limit. See, what do those things mean, and how do we flow with the logic with a formal definition with that idea? Well, we're going to look at that. And this definition is important for two reasons. First of all, it's important for you to be able to deal with a formal definition that has some sophistication about it. And the second thing is that the notion of limit is a real jumping off point for all of calculus. If you think of calculus as a grand oil well, then indeed the notion of limit is the wellhead. It's where everything starts in calculus. So you will look back upon this and say, limit is where it all started, you know, something like that. Well, the notion of limit, now here's what we're trying to deal with. We have the limit of f of x as x approaches c is L. L is the limit, c is this target point that we talked so many times about. And from a graphical standpoint, we're thinking about this. Well, here's our c value, here's our target point. We are thinking about approaching c from both sides. Our x values are approaching c from both sides. And the f of x values are approaching that limit, you see, often from top and bottom, as we'll see here. So as x approaches c, f of x approaches L, and that's what it's all about. Now, to understand the flow of this definition, though, I want to digress from limit. Forget limit just for a second, and let's go back to algebra and talk about the topic of graphing rational functions. You know, rational functions had the characteristic often that asymptotes were involved in those graphs. Now, asymptotes were lines that the graph gets infinitely close to at the extremes of the coordinate plane. Now, the extremes of the coordinate plane, that means extremely left, extremely right, extremely up, extremely down. And infinitely close means arbitrarily close. Let's suppose that here is such a graph. This is a graph of a rational function. Let's say that the y-axis here is an asymptote. So we know that the graph then gets infinitely close to that asymptote as the graph rises. In other words, as x approaches 0, f of x approaches infinity. Now, what does it mean for x to approach 0 and for f of x to approach infinity? How do we say that? Well, one way to say it would be like this. I could say, you give me a vertical distance, and I'll give you an x that corresponds with it. I don't care how big you choose your vertical distance. You might say, I'll choose 10. Okay, I'll choose 10. I'll choose this vertical distance. I'll say, well, this x. I'll choose this x. F of x is 10. You say, well, smarty, I'll choose 100. And I'll say, well, I'll get a little closer over here with my x, and f of that x will be 100. All right, that's one kind of way. We could go through that a few times, and then we might say, well, I'm going to let you choose a region. I'm going to let you choose a vertical interval up here. You choose a vertical interval, and I will give you a horizontal interval down here so that f of any x that falls in that horizontal interval will give us a value that falls in this vertical interval. Okay, now that is the flow for this definition. That is, we don't start with the notion of x approaching c. It's going to be involved, but we start with the notion of, let's take a distance from L. Let's take a vertical distance. Now, the distance we're going to call by a name. We're going to say that that distance is epsilon. All right, so this distance right here is an epsilon distance, and we want distances from L that would appear on both sides. All right, so we'll have that distance over here as well. Now, so here is this epsilon distance from L. And how does that correlate with distances or values of x down here? Well, let's see. We can just slide right over to our graph. Right over to the graph. And then right down to the x-axis. And we're going to call this region by a name, and the name we're going to call it is delta. So what we're saying then, lowercase delta. Now, what we're saying then is that if you give me an epsilon distance, then I can give you a delta distance such that if x falls within this delta distance from C, if x falls in this region, then f of x will fall in this region, this epsilon region around L. If I take this x, then f of that x will fall within that epsilon region. That's the whole idea. Let's look at the formal definition and see how it flows from this idea. Let f be a function defined on an open interval containing C. Stop right there. Why is the interval open? Why is it open? Well, remember that when we investigate the notion of a limit and a target point, the target point is C now, we want an interval around C from both sides. If we talk about a closed interval involving C or containing C, somebody is going to say, well, let's put C at the end of the interval. Well, we don't want to allow that, you see. We don't want to investigate only from one side. We don't want C to be the end of the interval, so we pick an interval that has no end. You see, we pick an open interval. Okay. So that's the purpose of the open interval idea. Now, this part about except possibly at C goes to the idea of defined. Let f be a function defined on this interval containing C, except that function may not be defined at C itself. We saw situations like that involving limit a little bit earlier. May or may not then be defined at the point C. And let L be a real number. Our limits, the limit number was a real number in the past. So under these conditions, we want to define the meaning of this idea. The limit of f of x as x approaches C is L. It means that for each epsilon greater than 0, vertical distance around L, for each epsilon greater than 0, there exists a delta greater than 0, delta distance around the target point C, such that we have this epsilon and delta, such that the x falls within the delta region. If x falls within the delta region, then f of x falls within the epsilon region. That's what this means. Now, why does this mean that? Why do these things mean what we say that they mean? Well, let's examine them carefully. This is supposed to tell us that x's that fall within, this is to define the x's falling into the delta region. X minus C, C the target point, x's in the neighborhood, minus C is less than delta. And there's an absolute value here. Why is that? Well, we want to make sure that this is a positive distance. And the 0 is less than this difference means that x cannot be equal to C. We disallow the idea that we're going to let x take on the value C, and that accommodates the notion that 0 is strictly less than this difference. So x cannot be C. Now, come back over here. Let's look at this situation in terms of falling within the delta distance. Let's examine it a little bit more. Suppose that our x is here. Then this x distance, this distance x minus the distance C, will give us this difference in their distances, and that difference falls within the delta amount. You see, the delta distance, and that's important. If we're choosing a value out here, then the x that is chosen will not give us a difference that falls within the delta region. So by saying that if the x has this characteristic, we are saying that x is in the delta region. All right, if x is in that delta region, then what happens? Well, f of x minus L is less than epsilon. That means that our f of x's are falling within the epsilon region. F of x minus L, the difference in those vertical distances, you see, will be less than epsilon. And we want absolute value to accommodate the notion that it doesn't matter which one is above or below the other one. We want to take absolute value because we're talking about distances, a positive amount. less than epsilon. So that's the flow of this thing. So we set up the situation up here. We have the limit idea. Then for every epsilon greater than 0, for every vertical distance that you can choose, this is the arbitrariness, you see, involved in this idea of limit. No matter how small you choose the epsilon, you see, no matter how little it is, there exists a delta, another little bitty region maybe, you see, such that if the x falls within the delta region, then the f of x is going to fall within the epsilon region. That's what it's all about. And this is to be, you're going to need to recall this, I'm sure. And you recall it from a fundamental understanding, from a conceptual understanding of the flow of it, and not from rote memory.